Good evening. Welcome to the 10th week of the live interactive session for the course on concrete technology. I am Sethi Vinayagam, a PhD scholar in the Civil Engineering Department at IIT Madras. Okay, let's start with an overview of the concepts that were covered in week 10. So, week 10 was about the durability of concrete and the different degradation process that affects the durability. So, there were three lectures. So, the first lecture, which is lecture 31. So, we were introduced to the concept of durability, right? We looked at the definition. So, it is nothing but the ability or the capability of the concrete structure or system, to the to provide some minimum performance, level when it is subjected to an environment where degradation of it happens, right? So in relation to that, we looked at concepts like service life. So what is service life? It is so because of this degradation, the performance of the concrete structure will keep reducing over time, and there will be one particular time when the structure is no longer able to perform its intended uh, function properly, right? So that when that limit is reached, that limit is called the serviceability limit, and when that limit is reached, we say that its service life is over, right? So it is that time it takes to cross the serviceability limit is called the service life. And then we also looked at the aspect of maintenance, right? So maintenance is nothing but the reversal of the the steps that you take to repair and to reverse the effects of the degradation, right? So to improve or to bring back the performance that is lost because of the degradation process, to extend the service life, we looked at the maintenance for that. And also then we moved on to look at different degradation processes. So we started with the sulfate attack, the seawater attack, right? So how sulfate attack degrades concrete. So we looked at how it forms gypsum and ettringite and leads to volume expansion and cracking. Then we looked at acid attack. So acid attack doesn't lead to expansion, but it causes dissolution of the hydration products. And then we also looked at the alkali aggregate reaction. And for all these processes, we also looked at how to prevent these attacks. And in the second lecture, we looked at other processes like the frost action. So the freezing of water that is present in the concrete, how that affects concrete. And then we looked at rebar corrosion, right? So when we looked at reinforced concrete, so the presence of chemicals like chlorides can when it reaches your reinforcements, it can cause corrosion. So we looked at the rebar corrosion in lecture 32, and then in the final lecture of week 10, we looked at carbonation. So which is the dissolution of carbon dioxide from the atmosphere into the concrete system, and how that also affects your reinforcements. And also finally we looked at chloride attack. Okay, so that's what was covered in week 10. Now we will look at some problems related to these. So the first question is, which of the following is most critical in the case of sulfate attack? So the options are magnesium sulfate, copper sulfate, sodium sulfate, and calcium sulfate.
বিলের কোনো একটা রোগ হয় কোনো কলের মানে বিদ্যুৎ ভেঙে দেবো বিল মানে কি আপনাদের কোথায় ছিল
Okay, the poll is launched. Okay, we have two votes for option A. Okay, so the right option is A. It is magnesium sulfate. Okay, so what is sulfate attack? So in the sulfate attack, what happens? So we have calcium hydroxide that is formed during our cement hydration process. So now when we have sulfates like calcium sulfate, when that is present, so what will happen is it will react with the calcium hydroxide and it will form gypsum, and this gypsum will react with the C3A in cement, and then it will form ettringite, which leads to volume expansion and ultimately cracking, right? So that is how the sulfate attack happens. But so we have different sulfates such as calcium sulfate, sodium and copper sulfates. So these so in comparison to these, when there is magnesium sulfate, what happens is that you will get magnesium hydroxide forming. So this magnesium hydroxide, what it will do, it will destabilize your CSH gel, right? So when CSH is destabilized, it will form MgSH, magnesium will form it. So but this MgSH is not having any binding property that you will see from CSH, right? So therefore your structure becomes destable, right? So therefore it is more critical than having other sulfates, right? So everything will attack, so everything will lead to cracking, but in this case it is also more severe because of this, because this CSH is broken and it is forming MgSH, right? So therefore option A is the right one. Okay, question 2 is select the component of cement which is attacked by sulfates. So the options are C3S, C2S, C3A, and C4A. Okay, so we have one vote for B and one for C. So the right option is C, C3A. Right, so as I said earlier, so in the sulfate attack, so we have both CaOH twice, so which is the calcium hydroxide, as well as C3A from the cement, which participates in the reaction, right? So what happens initially, we have sulfates like sodium sulfate or calcium sulfate and so on. And so initially it reacts with the calcium hydroxide and forms calcium sulfate, right? You get gypsum formation. And in the second step, so you have the C3A, so which will react with this gypsum that is formed to form ettringite, right? So that is the second part. So and this ettringite leads to so volume increase, volume expansion, and finally the disruption cracking in the concrete, right? So if you see it, it is the tricalcium aluminate which participates in this reaction, right? And therefore the right option is C, C3A. Okay, so question 3 is assertion reasoning. So assertion, chloride's attack does not generally cause expansion of the concrete. And the reason given is gypsum and ettringite are more soluble in chloride solution than in water. So the options are assertion and reason are true, and reason is the correct explanation of assertion. B is assertion and reason are true, and reason is not the correct explanation of assertion. And C is assertion is true, but the reason is false. And D is both assertion and reason are false. Okay, we have one vote for A. Okay, any other answers? Okay, we have two votes for A. The right option is also A, that both assertion and reason are true, and the reason is also the correct explanation of the assertion. Right, so what it says is chloride attack does not generally cause expansion of the concrete, true, as opposed to the sulfate attack that we saw, where because of the ettringite formation, we had the volume expansion. Right, in chloride attack, we won't see volume expansion. Why? Because in the reason given is the gypsum and ettringite are more soluble in the chloride solution than in water. So the reason is also correct, is that these two products, so in the chloride solution, because they are soluble, they will leach out, and because of that, you will not see any increase in the volume. Right, so we saw that. So this is predominant when you look at the seawater attack. So in seawater attack, even though sulfates are present in the seawater, but chlorides are also present in them. So because of the sulfates, you get the ettringite and gypsum formation, but they are soluble in the chloride solution, and therefore they will be leaching out of the system, right? And therefore you will not see the expansion. Okay, so therefore the option A is the right one. Okay, question 4 is the rate of disintegration in the case of frost attack is dependent on, the options are environment of exposure, curing age of the concrete, and all of these. Okay, we have two votes for option D, all of these. Okay, the right option is D, all of these, right? So when we looked at frost attack, so here R is the rate of disintegration. So R is a function of different factors. So one is the environment, so Cn is the factor for that, and C curing. So it also depends on the curing conditions, and C, age. So it depends on all the three. So the environmental factor, curing factor, and age. All these affect the rate at which the frost attack can disintegrate your concrete, right? So so it depends on your temperature. So that the environment will cover. So the curing condition, if you do good curing, so it can again reduce the frost attack. And also the age of hydration, it will also depend upon that, how much disintegration or how quickly it can happen, right? So all these, so basically it all the temperature and the porosity basically are the main factors. And so question 5 is the degree of AAR is least affected by. Options are presence of water, alkali content, concrete porosity, and bond to reinforcement. So the AAR stands for alkali aggregate reaction. Here we have one vote for A and one for B. Yeah, right option is actually D, bond to reinforcement, right? So here the question is about the factor which affects alkali aggregate reaction the least, right? So which is less important, right? So what's an alkali aggregate reaction? So in alkali aggregate reaction, so so it is a reaction between the silica content that is present in your aggregates and the alkali that is found in your cement, right? So it is a reaction between these two components in the presence of moisture, right? So that's when this alkali aggregate reaction occurs. So for this, as I said, it happens in the presence of moisture. So moisture is an important factor, right? So you need it for the reaction to occur. So it is affected by the presence of what? Alkali content. Yes, again it is unnecessary. So as the name suggests, it is the reaction between the alkali from the cement and the silica and the aggregate. So therefore you need alkali content. So the alkali content, the amount of it, so it will definitely affect your AAR reaction. And the concrete porosity, it is also important. So because so this will control your moisture content, right? So concrete porosity will affect your moisture. So therefore linked to the first factor, therefore C is also an important factor, right? So whereas in D, so the bond to reinforcement, so reinforcement, it does not really play a role here, right? So it is because it's a reaction between the cement and the aggregates, right? So reinforcement really does not play a role here. Therefore, this is the factor which least affects the alkali aggregate reaction, right? So the right option is D. Okay, so moving on to question number 6. The picture below shows the scaling deterioration of concrete. So it is a result of, the options are fluoride attack, sulfate attack, alkali silica reaction, and freezing and thawing. Okay, we have one vote for sulfate attack, one for freezing thawing. So the right option is D, freezing and thawing, right? So if you when we looked at reaction of frost, we saw that the type of damage that it can cause will result in surface scaling to complete disintegration because of the formation of the ice layers, right? So it will start from the surface and then keep progressing towards the depths of the concrete system, right? So here we are looking at one the effect as we see from the freezing and thawing effect, which is scaling, right? So therefore the right option is D, it is freezing and thawing. Okay, question 7 is the corrosion kinetics is best controlled by, the options are high alumina cement, ordinary Portland cement, by changing the type of aggregate, and option D is blended cement. Okay, so we have one vote for A and for D. The right option is D, use of blended cement, right? So what happens? So here we are looking at corrosion kinetics, right? So it is about how quickly the corrosion reaction occurs, right? So for corrosion to occur, so what happens? What should happen is the chloride should reach your rebars, right? Uh, so how will that be affected? So if we look at the different types of cement, so we are looking at what is the chloride diffusion coefficient. So we have OPC, so which has 44.7, SRC 100, fly ash plus OPC, slag plus OPC 114 and 4.1. So what we see is that in the case of blended cement, which is the use of fly ash and slag, so we see that the chloride diffusion coefficient is smaller. Why? Because your pore structure will be better. Your micropore structure will be improved when you have blended cement, right? So it's not easy for chloride to reach your reinforcement. So because of that, you will have better resistance to the corrosion, or the rate of the corrosion will be much slower in that case. Right? So therefore, the right option is the use of blended cement. Right? So your aggregate is not going to impact much, right? So therefore, changing aggregate is not a way of controlling it. So OPC again for the same for the reason that was explained now. So it's not as good as a blended cement. Alumina cement, again, alumina content is not affecting your chloride attack, right? So it's important in the case of sulfate attack, but not for chloride corrosion type, right? So therefore, the right option is D. Okay, question 8 is the chances of corrosion of reinforcement is drastically increased when concrete fully immersed in water. So we have to say whether the statement is true or false. We have two votes for option A saying it is true. Okay, so actually this is a false statement. So what's given here is chances of corrosion dramatically or drastically increases when it is fully immersed in water. Right? So, so we need to understand what is so how or what are the requirements for the corrosion to occur. So for corrosion to occur, so we need two things, which is oxygen and moisture, right? So both are necessary for corrosion to occur. So, but here we are looking at a situation where it is fully immersed in water. So what happens? So when you have fully saturated, so in that case you will not have, so you will have moisture, but you will not have access to oxygen, right? So because of that, so one of the components that is required is eliminated. So because of that, you will not have, you know, accelerated corrosion, right? So even that would be corrosion occurring, but because it is fully immersed, you will not have accelerated corrosion as given in this statement. So therefore, it is false. Okay, question number 9 is to protect concrete against frost attack. Which of the following can be adopted? The options are air entrainment. Option B is low water cement ratio. Option C high water cement ratio. Option D is good curing. Okay, so this is a multiple select question. So more than one option could be correct. Okay, we have two votes for options A, B, and D. Okay, so the right option is also uh, all the three A, B, and D. So we already saw what are the factors which which control or which are related to frost attack. So we said one is the environment, curing conditions, and also the age, right? So in relation to that, we have so these factors which help us in controlling the effect of those factors. So we have air entrainment. So air entrainment, how does it affect? So when you have this so what happens in the frost attack? We have the water in your capillary pores freezing, and this frozen water will cause pressure in your nearby pores that are connected. So when you have these or water that is in the nearby pores. So when you have air entrainment, what will happen is you have air voids which does not contain water, and so these air voids so when they break, so they will release some of the pressure that is built because of this frozen water, right? So because in that way they will help release the pressure and delay or postpone the effect that we will see other. So that is for air entrainment. For low water to cement ratio, when you have lesser water to cement ratio, your porosity will be controlled, right? So you'll have less pores, right, and that will also improve your resistance to the frost action. So because of B, C is opposite of it, so it is not right. And D is good curing condition. Again, you have when you have good curing, because of that you have better hydration, right? So better hydration, you have control over the porosity, and therefore it will also help you improve uh, um, you know the effect against the frost action, right? So therefore all the three can help you prevent frost, the effect, control the effect of frosting, right? So therefore A, B, and D are the right options. Okay, question number 10 is, what is the main reason why ettringite formation is a leading cause for the deterioration? So the options are, it occupies more volume for the same weight as CSH, it causes immediate cracking, it causes displacement of the elements, and it causes white residue to form in the cracks. Okay, we have two votes for option A. So the right option is A. So it occupies more volume for the same weight as the CSH. So we already saw this when you looked at sulfate attack. What is the reaction that occurs, right? So finally, it forms this ettringite. So what happens is that your mass will be conserved in this reaction, right? So whatever is the reactants, so the weight of that will be the same as the weight of the product, right? So WP and WH. But what is different is that the volume. So the weights are equal, but the volume of your the reactants are, so the volume on the left hand side. So that will be lesser than the volume of the product that is formed, right? So because of this, so this is the cause. So because even though the weight is conserved, so the volume is actually increasing. So because of that increase in volume, so you will see the crack formation. So the crack formation is the effect, and the cause is the increase in the volume, right? So therefore, here we are asking what is the reason for the or the cause, right? So therefore, A is the right option. Okay, so question 11 is, seawater attack is characterized by, the options are excessive expansion and spalling. Option B is severe leaching of chemicals. Option C is undissolved salts in fully submerged areas. And option D is rebar corrosion. Again, this is a multiple select question. Okay, so we have one vote for options C and D and one for B and D. Okay, so the right options are both option B and option D, right? So seawater attack. So we already saw what happens in this seawater attack. So it is so there will be both sulfate as well as chlorides, right? So it is generally present. So what happens? So sulfate attack we saw it leads to the ettringite and gypsum formation, but we also saw because of the chloride formation there will be and the dissolution of the ettringite and gypsum in it and leads to leaching, right? So B is one effect that we see. It is the leaching of the chemicals, right? So B is the right option. And the other problem is because of the chloride. So because you have chloride, so when it penetrates and reaches your rebar, so it can lead to rebar corrosion, right? So that is the other effect that you see in the seawater attacks, right? So rebar corrosion can also occur, right? So therefore these two options B and D are characteristics of the seawater attack, right? Okay. So question 12 is acid attack becomes severe at a pH level less than dash. So this is a question where you have to use the chat. So you can type your answer in the chat. We have one answer as 4.5. Okay, any other answers? Okay, so the other answer you got is 9. Okay, so we'll look at the right answer now. So the right answer is actually 4.5. Right? So here we are looking at acid attack. So which means that the pH has to be less than 7, right? So in that case only it will be acidic, right? So but your acid attack will be starting, right? So it will be initiated. So when your pH is below 6.5, when it goes to less than 6.5, that's when the acid attack starts, right? So but here we are looking at when it becomes more severe. So when your pH drops further, so which means what your acidity is increasing, right? So as you go towards 0, right? So therefore, it becomes more and more acidic. So when it falls below 4.5, so in that case, you will have more severe effects, right? So therefore, the right option is 4.5. Right? So when you have more than 7, it is alkaline situation. In that case, you need not worry about. But when it becomes acidic, so less than 6.5, that's when your acid attack will happen, and when it is dropping below 4.5, it will become more severe. Okay. So moving on to question number 13 is the concrete barricades on a flyover. So as shown in the figure, it has these cracks. So what is the reason this could be? The options are it is due to alkali silica reaction. Option B is sulfate attack. Option C, chloride attack. Option D is acid attack. We have one more for A, alkali silica reaction, and one for B, acid attack. Okay, so look at the option, right option. So right option is A, alkali silica reaction, right? So what we saw in the alkali silica reaction, so it will result in a type of cracking called as map cracking, right? So as this was one example picture that we saw. So this kind of cracking that we see, where there is a network or a series of cracks, that are interconnected, right? So this kind of cracking is called as map cracking, right? Like a network or a web of cracks on the surface, right? So this kind of cracks is formed by the alkali aggregate reaction that is occurring, right? So this occurs not in the initial stages, but after few years, of after construction, right? So that's when we see this kind of cracks because if this alkali aggregate reaction is occurring, right? So in this given example also we see the similar pattern, right? So these kinds of interconnected cracks. So these are map cracks, and therefore this is resulting from the alkali silica reaction, right? So the right option is option A, the alkali silica reaction. Okay. So question 14 is freezing of water and concrete occurs in both capillary and gel pores. So we have to say is this statement true or false? Okay, we have one more for option B. The right option is B. It is false. Why it is false? Because the statement says that freezing of water occurs both in the capillary and gel pores. Right? It's not true. It is only in the water in the capillary pores that will freeze, not in the gel pores. Right? So it is not both. It is only capillary, right? And even within the capillary pores, it is not all the capillary pores that will freeze at the same time. So the freezing in the even in the capillary pores will be occurring at different temperatures, right? Why? There are different reasons because when you have the presence of salts, your freezing point will go down, right? It will not always freeze at 0 degrees, right? And also the size of pores will also affect your the freezing temperature, right? So therefore there is no single freezing temperature, a single freezing point, and also within gel pores you will not see freezing, right? So because of this, the right option is that statement is false. Okay, question 15 is dash concrete and dash concrete does or do not exhibit significant rebar corrosion. So under which conditions concrete do not exhibit rebar corrosion? is with respect to two conditions of concrete, two different environmental conditions. Okay, any answers? We saw this before under seawater attack. Okay, so we'll look at the answer now. So the right answer is that completely dry and fully saturated. So in these two conditions, we will not see corrosion. Right? So why? Because what happened. So as we saw earlier, so there are two requirements for this corrosion process to occur. Right? So let's look at it. So we have oxygen, right, and also we need moisture. Right? So these two are requirements, and so under different conditions, you have the rebar corrosion represented as the can occur or not occur. Right? So what are the different conditions? So one is we have the totally dry condition, right? So the other could be fully saturated, right? So the other is partially, wet, right? So when you have fully dry or completely dry, so what you will have
you will have oxygen, but you will not have moisture because it is dry. So because one of these two components is missing, so you will not have debar corrosion. So the other is fully submerged. So in that case, you will have moisture in plenty, but you will not have oxygen. So therefore, in that case also, it is not conducive to corrosion occurring. So when it is partially wet, so or partially, it's not completely dry. In the between case, so you will have both oxygen as well as moisture, and therefore corrosion will occur. Right. So in these two conditions, so they're completely dry and the fully saturated, we will not have significant corrosion occurring. Right. So therefore, those are the correct. Okay. So question 16 is the depth of penetration of carbon dioxide in concrete is proportional to dash. Okay, the hint is it is a mathematical function of the time elapsed or the time it is exposed. So how is it related to the depth of penetration? Any answer? All right. So we'll look at the answer now. So the answer is that it is proportional to root t, right? So if x is the depth of penetration, right? So then x is proportional to square root of the time that it is exposed to the environment, right? So this is one of the carbonation models that we saw, is that so x is equal to kt, so the proportionality constant is k, so it is proportional to root t, so it varies as a function of root t. So this we saw that so the depth of the carbonation is actually driven by the gradient in the CO2 concentration, right? So in the atmosphere or outside, you have a concentration C0 that is in excess, higher concentration, and within the concrete, so you'll have a concentration of Cc, which is lower, and it is this difference in the concentration gradient which will drive this process, right? So and if you derive the flux, uh, so which is the rate of flow across this unit, if you take a unit area or a unit depth, some infinitesimally small depth dx, then you can derive what will be the flux, and finally you will see that the depth of the carbonation is dependent on the time, so which is the exact function is it will be root t, right? So it will be proportional to root t. Okay, so question number 17 is the acid soluble chloride indicates the free chloride and the water soluble chloride indicates the total chloride. Is this statement true or false? So let me create a poll. Poll is launched. Okay, any answer? Okay, we have one vote for B, false. So the correct option is B. It is false. Why? Because so when you look at the total chloride in concrete, so you can divide that into two components, which is the free chloride, right, and then the chemically combined chloride, right. So we have some chloride which is chemically bonded. So for example, with different elements. For example, here it is given with C3A. So you have some chloride which is bonded chemically, right? So this chemically bonded chloride. So this cannot be this cannot be removed with water, right? So it will not be soluble with water. It's only the free chloride which will be soluble in water, and then it can be removed, right? Therefore, for this chemically bonded chloride to be removed, so you need to break this bond. So for that, so therefore, it is only soluble in acid, right? So therefore, so and also this free chloride can also be removed with acid. So when you find the total chloride content, so it is what is soluble in acid, and when it is the free chloride content, it is what is only soluble in water, right? So therefore the given statement is the opposite. So it says that the free chloride is only what is soluble in acid, and what is soluble is total chloride. That is the opposite. So acid soluble is the total chloride content, right? And then the free chloride is actually water soluble, right? So therefore, the right option is that the given statement is false. Okay, question 18. This is a numerical problem. So if the carbonation depth in continuously moist but unsaturated concrete after 8 years is 12 mm, what will be the likely depassivation time for the rebar if the clear cover depth is 40 mm? Right? So the options are 91.23, 88.88, 85.42, and 81.66. Any answers? Okay, so we'll look at the answer now. So the right option is actually B, 88.88. All options are in years, so 88.88 years. So before we look at the solution, let's try to understand what's asked in the question, right? So what we are looking at it is about the effect of carbonation, right? So the carbonation depth is what we are interested in. So the concrete that we are looking at is exposed to continuously moist but unsaturated condition, right? So for carbonation, so two things are necessary. So like we looked at for corrosion, how oxygen and moisture both were required. So for carbonation to occur also, so you need some moisture and also exposure to CO2, right? So if either of them is absent, so then carbonation will not occur. So again, same as earlier. So if it is completely dry or if it is fully saturated, so you will not see carbonation happening. So it should be somewhere in between. So which is the case here? So we have some moisture which is continuously present, but it is also unsaturated, right? So which means the pores are not fully occupied by water, right? So there is some carbon dioxide that can penetrate into your system, and there is also moisture present, so carbonation will occur, right? And we are also given that after 8 years, so the carbonation has occurred up to a depth of 12 mm in the concrete, right? So that is initially. Now what the question is, so what is the likely depassivation time for the rebar if the clear cover depth is 40 mm, right? So what is depassivation? The depassivation time is nothing but the time it takes for the carbonation depth to reach the rebar level, right, such that the once you have reached the rebar, so what happens that it is now exposed, and therefore it can now start corroding your rebar. So your rebar will be exposed now. So that is what we call as the depassivation, right? So depassivation, so your cover, the clear cover, it is providing resistance to corrosion, and once it is totally removed, so we say that it is depassivized, and therefore your corrosion can now occur. So we need to find the time it takes for this to occur, right? So we have our concrete system. So we have some rebar within that. Let us say this is it, right? So what is your clear cover depth? So it is from the outer edge of your rebar to your top surface, right? So this is totally 40 mm in our problem, right? So you are starting from the top. So it will start from the top here because this is exposed to your environment. So the carbonation will start from the surface, and with time we saw that it is we saw one carbonation model how it occurs. So with time it will slowly it will start penetrating in, and therefore there will be one particular time at which your rebar will start getting affected, right? So that is the time that we want to find, right? Now let us see how to find that. Let me reshare. So the carbonation model that we saw earlier. Okay, so what was it? It was x was equal to k times square root of t, right? So x here is the carbonation depth, and t is the time, and k is some proportionality constant, right? So this is how the carbonation proceeds. And now we are having two scenarios. One is the initially after 8 years there is a carbonation of up to 12 mm, right? So that is one scenario. So where x is 8, x is 12 mm, where the depth is 12 mm, and this has occurred over a period of 8 years, right? So this is one equation that we have. So equation number one, let me put it like this. So the other one is, so what is the time it will take for 40 mm to be carbonated? Right? So in this case, we know the depth, which is 40 mm, but we don't know the time it takes. Right? So it is square root of, let us say, the unknown as t. So this is the second situation or the second scenario. So we have these two scenarios. Now, how do we find out what is t? So we have two variables, k and t, and we also have two equations. So therefore, we can solve this. So if we just divide equation 1 and 2, so what will happen? We'll have 12 over 40 is equal to, because we are dividing it and k is the same, so it will get uh, cancelled out. So we'll have square root of 8 by t. Right. So once we divide the two equations, this is what we have. So this is now simple to solve. So what you will have? You'll have 12 by 40 squared times 8. Right. So that's what your t will be. So 12 by 40 the whole square, actually not just 12 square, is equal to 8 by t. Right. So from this, if you solve it, you'll find that t is 88.88 or 89 years. Right. So that's how we find how long it takes for the clear cover to be totally depacified. Okay, any questions? Okay, if there is no question, we'll move on. Yes, question 19 is the threshold chloride content is influenced only by the type of steel used and not the cement type. So is this statement true or false? Okay, we have one vote for B. So B is the right option, so it is false. So what are we looking at? So we are saying that threshold chloride content is influenced only by the type of steel and not the cement type. So what is threshold chloride content? It is that amount or that content of chloride. So at which your corrosion will start. It's where your corrosion starts of your rebar, right? So that is what we call as the threshold content, and this threshold content is not it's not constant. So a variety of factors determine what the threshold chloride content is, and one of it is this type of steel that is used, right? So because steel, the reinforcement, it is what is undergoing corrosion. So the type of steel that we are using will surely determine what is the chloride content at which it will start getting corroded. But it is not only that, other factors including the cement type, the amount of C3A, the mix proportioning, and also the source from which this chloride penetration is occurring. All of these factors together, they will determine what is the threshold for this chloride content. Right? So it's not just the steel type, but also a variety of other factors. Right? So therefore, the given statement is false. Okay. Question number 20 is a concrete roof slab as shown in the figure. This is as shown in the figure. So what is this a result of? So the options are chloride attack, sulfate attack, rebar corrosion, and cracking due to excessive load. We have one answer for option A. The right option is option B. It is due to sulfate attack. Right. So what are we looking at? We are looking at some formation of white powders on the surface of the slab. Right. So this is the symptom of a sulfate attack. So where we'll have white powders of the gypsum along with some other powder formation which will be visible when you scratch the surface. Right. So this is what we see from the sulfate attack. Right. So we saw that sulfate attack results in the formation of gypsum and anthracite, and this gypsum powder, which is white, will be formed on the surface, right? So that is a symptom that you can use to identify the sulfate attack, right? So which is what we are seeing in this figure given. So it is option B, sulfate attack. Chloride attack is about the rebar getting corroded, right? So this is the right option is B, sulfate attack. Okay, question 21 is the presence of which of the following has no effect on the alkali silicate reaction or the alkali aggregate reaction. So the options are opal, calcite, chalcedony, and tridamite. We have one vote for option B, calcite. Okay, so the right option is B, it is calcite. Okay, so what are we looking at? We are saying we are talking about the alkali silica reaction or the alkali aggregate reaction, and we are saying which of these has no effect. So no effect means it should not participate in this reaction. Right. So for that, what should happen? So for this alkali aggregate reaction, so we should have some reactive or the active silica content that should be present in the aggregate, right? So which will react with our alkali in our cement, and then that will result in your alkali silica reaction happening, right? So these two are important. So one is the alkali content, and other is the reactive silica content, right? So we have different types of aggregate, and so if it has to have no effect on the AAR reaction, which means that it should not have this uh, silica which is reactive. So for that, so we saw that examples of these different forms, which are opal, chalcedony, and tridamite. So these contain the reactive silica in them, and therefore these will participate in the alkali reaction. Right? So it is calcite which does not have this active silica, and therefore it will not participate in that reaction. Therefore, the right option is B. It is calcite. Okay, question 22 is all the water present in the concrete pores freezes below 0 degrees Celsius. Uh, the options are true and false. We have one vote for option B, false. Yeah, the right option is B. It is false. Like we saw this before in the air when we were talking about the frost action. So there is no single freezing point for water in the concrete. So why was that? Because the water in the cement, it contains salts and also at different concentrations. Right. So the presence of salts will lower the freezing point further, and also because of the concentration that will be different at different regions. Right. So therefore, not all water will freeze at just when the temperature reaches 0 degrees, and also not everywhere, even when the freezing point at some region is reached, it will not freeze everywhere, right? So because of the difference in the concentration, and also the other factor is the pore size. So in fine pores you will see freezing at a much lower temperature, right? So therefore it will not happening uh, you know uh, it will not be freezing at freezing of all the water present, right? So it will be some if it is pure, it will freeze at 0, otherwise it will not, right? So therefore the given statement is false. Okay, question 23 is what are the different preventive measures against the sulfate attack? So the options are low C3A cement, option B is blended cement, option C is both A and B, and option D is none of these. We have one option for C, both A and B. So the right option is also C. It is both A and B. So what are we looking at? We are talking about sulfate attack, right? So sulfate attack. So you need so to prevent it. So how does it occur? Because of the intrusion of sulfate into your system, right? So how can we prevent that? So and once the sulfate attack happens because of the reaction with C3A, right? So because of the formation of yttrium. So one is we can control this reaction. So by reducing the amount of C3A present, so the amount of yttrium that is formed can be reduced, right? So therefore mitigating the effect. So that is one perfectly valid solution. So we can go with a low C3A cement, right? So this is what we have in a sulfate resisting cement. The amount of C3A will be lower. So the other option is to prevent, the sulfate, intrusion in the first place, right? So therefore the reaction cannot occur. So for that we need to control the porosity. So blended cement, in blended cement you'll have, better, porosity. You'll have lesser pores. So blended cement will also have resistance against the sulfate attack. So both A and B are, perfectly valid measures that we can have for preventing the sulfate attack. So the right option is C. It is both A and B. Okay, question 24 is what are the preventions against the alkali aggregate reaction? So the options are prevention of moisture contact uh, and the use of cement with low equivalent alkali content, the use of inert aggregates, and all the above. We have one option for 4. Okay, any other answers? Yeah, we have 2 votes for option D. The right option is D. It is all the above. So we are talking about alkali aggregate reaction. So for alkali aggregate reaction, as we saw earlier, we need the alkali content present in the cement and also the silica from the aggregates. And also you need this reaction occurs in the presence of moisture, right? So all these three conditions need to be satisfied. So for this reaction to occur, so if we by preventing or by restricting any one of this, we'll be able to prevent this from happening. So by so we can prevent moisture from our country. So by preventing that, we will be able to stop this reaction. And B is using cement with low equivalent alkali content, right? So because alkali is needed, so by using cement that has lower alkali content, so we can also control the alkali aggregate reaction. And the third is the use of inert aggregate. So right, so as we saw some examples before of this reactive aggregates. So by not using them, so by going with inert aggregates, so we can again reduce the effect of the alkali aggregate reaction. So all the three A, B, C are valid prevention measures. So the right option is D, all the above. Okay, question 25 is depassivation of reinforcement indicates the end of physical life of a structure. Is the above statement true or false? Okay, so we have two votes for option B, false. Okay, the right option is B, it is false. So what is the statement saying? So it is saying that the depassivation of the reinforcement indicates the end of physical life of a structure. Right. So we need to know these the the meaning of these two terms. One is what is the depassivation, and also the other one how we will find out or what do we mean by the end of the physical life, right? So depassivation is what? So when you have uh, the reinforcement, so you'll have some protective cover, right? So it will not immediately undergo corrosion, right? So it will take some time. So once this protective layer is totally removed and it is exposed, and when corrosion starts occurring, so that's what we call as the depassivation, right? And so once that is occurred, you will have corrosion occurring. And then the other one is the physical life, the end of physical life. So it is when the structure no longer is able to serve its purpose, right? So when that is the case, so that's when we say that its physical life is ended, or its service life is ended, right? So that's the two things. So here we are saying that this end of physical life is the same as this depassivation occurring, right? So but it is false. Why? Because so let's look at this chart. So it is showing what is the degradation as a function of time. So we have some initial period. So this period represented by TP. This is what we call as the depassivation time. So it is so until this point there is no corrosion that is occurring, right? So there is the passivation layer is slowly being removed. So once that is totally gone, you will see that corrosion occurring, right? So on that, so for some time, so you, because of this corrosion, so you'll have degradation, and there will be at one point where you will see cracks occurring, right? So that point when it starts forming cracks, so that is what we call as the end of life or the end of service life, right? So that is the end of life. So here, what the statement is saying is this particular time, the depassivation time (TP), this is the same as the end of service life, right? But it is false. It is the sum of both depassivation as well as this time it takes to corrode, TC. So TP plus TC, that is here end of service life. It's not at the end of TP. Okay, therefore this statement is false. Okay, any questions? Okay, with this question, we come to the end of today's session. Okay, if you have any questions or doubts, you can ask. Thank you. If you have no questions, we will meet again next week, same time. Okay, if you have no questions, you can feel free to log out and just stay back in case you have any questions. Thank you. Okay, so if there are no further questions, we'll close the session here. We'll meet again next week. Thank you.